Alright guys, today this is energy part 2. You've already completed part 1, so we're going to get started. There are Cornell notes that correspond to this, so make sure that you are using them to complete the activity. So today we're going to talk about energy conversions or energy transformations, and what needs to be understood is that energy can be converted or changed from one form to another. And remember, energy is never lost or destroyed in the process. It just transforms to another type. For example, the food that you eat has chemical energy, and when you eat that food, the bonds in the atoms are broken and the energy is released into your cells. So your body is able to use this chemical energy and change it to kinetic or mechanical energy, energy of motion, like when you move, you run, you jump, whatever you do. And ultimately your body is going to create heat energy or thermal energy because of the motion or the movement that you are doing. You need to think about the energy conversions that take place, for example, within a flashlight. So we all know that you put batteries in the flashlight, and batteries are connected to wires. And when you flip the switch on your flashlight, these battery actually connects totally, and then you get that light, and ultimately with that light comes heat. So that would be an example of energy transformation that occurs within a flashlight. We got chemical energy, wires, all wires indicate, and plugs, things like that are electrical energy. And then light and heat is, of course, if we remember, the electromagnetic spectrum had visible light and, not ultraviolet, infrared, when we identified infrared waves as heat. So this light and heat are both forms of electromagnetical energy. But in some instances, you might see people just write for this energy conversion of the flashlight. The batteries are chemical, the wires are electrical, and the light energy, they would put radiant, or they might just put heat energy. In some instances, that would be thermal. But truly, those are forms of electromagnetic energy. So in your notes, go ahead and label the energy conversions in your notes. It's electrical pencil sharpener. Of course, they've already given us a hint. It's electrical, so meaning that it plugs in, and then it has turning gears and blades. So those turning gears and blades would be energy of motion. So if you got electrical energy for the wires and mechanical just means moving, like kinetic, you've got that correct. Okay, what about a heating pad that plugs in? So we know the wires are electrical, and the heat, what did we just say the heat is? Thermal, and that's what it's going to label this one as, thermal energy. What about a plant? Plants do photosynthesis, and so plants get their energy from the sun in order to change that energy into food for themselves. Remember, those are our producers. They can produce their own food. So the sun would be what form of energy? You could put electromagnetic. Most people would put radiant. Let's see what we got. Electromagnetic. Like I said, radiant is sometimes also a choice. So we got electromagnetic energy that goes into the process of photosynthesis. Remember, photosynthesis requires carbon dioxide, water, and sunlight. So all of those things produce a what kind of change? A chemical change. So if you said chemical energy, you were absolutely correct. All right, so let's look at some of these energy transformations. A change from one form of energy to another is called an energy conversion. We usually refer to those as energy transformations. So I'd like you to remember it as a transformation, even though conversion pretty much means the same thing. It's converting or changing energy from one form to another. Most forms of energy can be converted into another form. We know that because we do it all the time. So they're giving us an example of a toaster that plugs into the wall, and the toaster is going to convert that electrical energy. Hello? Sorry guys, that was we're interrupted. Okay, so we were at the toaster, so that you use that electrical energy and it transforms into that thermal energy as it toasts your bread. If you wanted to get real specific, you can see the coils inside the toaster light up, so it could be light and heat energy. But think about your food, the food that you eat. You need food in order to get chemical energy. That's the chemical energy you get from eating food. Actually allows you to do all your bodily functions. So without this chemical energy, you would not be able to do anything. So that's highly necessary. All right, let's look at conversions between potential and kinetic energy. Potential energy is stored energy an object has due to its position. So if you raise something high off the ground, you are giving that object potential energy. The higher up the object is, the greater the potential energy. So if you can see on this image here, it shows the greatest potential energy at point 1 and point 5, because at those points are the highest points of the pendulum. Okay, the fastest an object moves, where it's at its fastest, usually at the bottom, here it's at point 3, that has the greatest energy of motion. So imagine you picked up the marble on the bottom of the pendulum and raised it up. You're giving it its greatest stored energy because you put energy into it by raising it up. So it has its greatest potential or stored energy. Then you let it go. It's moving the fastest when it gets to the bottom of the swing, and that is when it has its greatest energy of motion, which is referred to as kinetic energy. So what you also need to realize is, so potential energy is that stored energy you gave the pendulum by lifting it up to allow it to swing. So at number 1, we have our greatest potential energy, and at 3, the greatest kinetic. But as you look at that, stored potential energy is going to change into kinetic energy as the pendulum is released. So stored energy changes into kinetic. And at one point in the diagram, or in the motion of any object, the potential and the kinetic energy are equivalent. It's kind of like a seesaw. When the potential energy is high, the kinetic energy is low. But when the kinetic energy is high, the potential energy is low, because you use that stored energy to create motion. But at one point in the seesaw, they're even. And that's where potential energy is equal to kinetic energy. And that's noted in the diagram on points 4 and 5. So if you read at the top, it says at the midpoint between the greatest potential and the greatest kinetic, potential and kinetic are equal. We can do the same thing with a waterfall here. At the top of the cliff, the gravitational potential energy is the greatest, the potential energy, because that stored energy at the top is, because it's up high, it has the most gravitational potential energy. So once it begins to fall, the fastest it's moving is at the bottom. So that means it has its greatest energy of motion, or greatest kinetic energy, at the bottom. But in the midpoint between the two, they would be equivalent, potential and kinetic energy, because it's like a seesaw. One goes up, one goes down, and when you're doing the hands up and down, they meet in the middle, and that's where they're equivalent. So it says the water at the top of the fall has the greatest potential energy because it's higher than at the bottom. The higher up you are, the greater your potential energy. As the water falls, its height decreases and it's losing that stored energy because it's in motion, and it's converting that stored potential energy into energy of motion, or kinetic energy. So the kinetic energy is increasing because the speed is increasing. And as we said, in the middle and midpoint, they would be equivalent. So the laws of conservation of energy are real similar to what we learn in chemistry about the laws of conservation of mass. Remember, what goes in must come out. And this is the same thing, not only with the atoms of matter. When we did chemical reactions, and we said, oh, if it has a mass of 10 grams, the reactants, the things that are going to go into the reaction, they're going to come out with a mass of 10 grams because what goes in must come out. Same with energy. Energy can't be created or destroyed. What goes into as potential energy will come out in the end as kinetic energy. So it's the total amount of energy is always going to be the same going in and out of any changes. So, and also a good note here, it says when you hear or read about conserving energy, that means just being frugal about what energy you utilize in your home, like not leaving the lights on or things like that. It's not really the same as when we talk about law of conservation of energy, which means what goes in must come out. So when you're conserving energy at home, it means you're just saving energy and not wasting it. All right, there are two types of energy. We know that. There's potential energy and kinetic. Potential is that stored energy, and kinetic is energy of motion. But energy we use today comes from a variety of sources, such as fossil fuels. Remember, anything that was created long time ago by fossils breaking down, like coal and oil and natural gas. Those are fossil fuels, but we also use energy sources such as nuclear power. We use the sun for solar energy. We use wind energy. Geothermal is the heat of the earth, and hydropower is just water, the motion of water, to create energy. Most of these forms of energy that we have, we convert into electrical energy. There are 7 forms of energy that you need to remember, and one way to remember that is rectums. So RECTMNS, rectums, which stands for radiant, electrical, chemical, thermal, mechanical, nuclear, and sound energy. So if you know those, that'll help you understand what forms of transformations are taking place. Like we said, for example, photosynthesis, taking solar energy or radiant energy and transforming it into that chemical energy in the plant, that chemical energy the plant uses to make its own food, for example. You'll get better at this. This is not so hard, but remember rectums, okay?